Okay, so now we're going to talk about the ideal gas laws, and what we have seen is that there's a relationship between volume and pressure. You know, volume is directly proportional to 1 over pressure. Volume is directly proportional to temperature. Of course, that assumes Kelvin. Volume is directly proportional to the number of moles. If I combine all these, I get NT over P is directly proportional to V. And if I want to replace this proportionality constant, I need to find a constant that makes that equation true. And that constant is known as my ideal gas constant, capital R. Okay, so depending on my units for pressure or volume, my R units change. Now the two that you need to know for the AP exam, they're both on the sheet, but again, if you're taking the multiple choice, you have that sheet. So basically, most of the gas law problems use this, 0.08206, and it's liters atmospheres over mole K. Now, if you are dealing with energy, if you need joules, if you're dealing with energy, the R will switch to 8.314. Okay? Now, what you need to always make sure of is if you're using this 0.08206, that you have your volume in liters and your atmospheres, your pressure is in atmospheres, and of course you have temperature in Kelvin, because you would never think of not doing that. So we end up with this equation, as you know, is PV, PV equals nRT. Alright, so let's go ahead and use our PV. Okay, so let's just pause here for once. Okay, so calcium carbonate decomposes upon heating to give calcium oxide and CO2. We have a sample of calcium carbonate. It is decomposed, and the carbon dioxide is collected in a flask. After the decomposition, the gas has a pressure of 1.3 atmospheres and temperature of 31, and we want to know how many moles of gas. Okay, so we can use PV for this. PV equals nRT. I want to solve for moles, so moles, if I divide both sides by PV, I get, or divide both sides by RT, I get moles is PV over RT. So let's fill in what we know. So we know this is 1.3 ATM. We know volume is 250 milliliters. Now I need that in liters in order to use my R of 0.08206, right? Because that is liters atmospheres over moles K. Okay, 1.3, so this is 0.250 liters over my R, which is 0.08206 liters atmospheres over moles K, times my T. Now my T is 31 Celsius, and if I add 273 to get to that, I get 304 K. 304 K. So my K cancels there. My atmospheres and liters will cancel on, end up with units of moles. Okay, so if I punch this, I'm going to get 1.3 times 0.25 equals, divide by, in parentheses, 0.08206 times 304, close parentheses, and I get 0.013 moles of CO2. And it looks like I want two sig figs, 0.013 moles. Okay, let's take a look at another. Okay, a gas pressure in an aerosol can is 1.5 atm at 25 C. Assuming the gas inside obeys the ideal gas equation, what would the pressure be if we heated the can to 450? Okay, so it talks about the ideal gas equation, but in fact that's not really what you need here. What we have is change in conditions. We're starting at 1.5 atm at 25 degrees C, which is 298 K. And we are heating it up to 450, which is 273. So this is really a gas law problem, not a PIV nerd. So that's 723. It goes up to 723 K. And wants to know what's happening to my pressure. So all I have to do is take my pressure of 1.5 atmospheres. And these laws assume ideal behavior, right? Which is what it's really talking about here. So if my temperature goes way up, my pressure will go way up. So I want a factor to make it go up. And that's going to be over 298K. And if I punch all this, I end up with 1.5 times 723 divide by 298. Oops. 298, and I get 3.6. I want 3.6 ATM.